Problem that I truly adore. 2568 minimum impossible or. So you're given a zero indexed integer array nums. We say that an integer x is expressible from nums if there exists some integers, blah, 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 for which the oring of them mutually together results in x. So, in other words, an integer is expressible if it can be written as the bitwise or of some subsequence of nums. Okay, so you have nums. You can select any number, any set of number in nums, any subsequence of the numbers in nums, and OR them all together and get some number. X is expressible if you can select any of those numbers, any ones you desire, and create X from it. Return the minimum positive non-zero integer that is not expressible from nums. Okay, so for example, in this example here, we have nums equals 2 and 1. Well, 1's not going to work because 1 is in nums. 2's not going to work because 2 is also in nums. 3, you say, well, 3 is not in nums. Well, 3 equals 2 or 1. So that's not going to work. And then finally, you try 4. 4 is going to work because 4, there's no way that you can take 2 or 1 or 2 or 1, right, to get 4. So 4 is not expressible in nums, so this is what you would end up returning. In this next example, we have 5, 3, and 2. It'll become pretty intuitive in a moment, but you can't create 1 from 5, 3, and 2, right? That's just the nature of how OR works. You can't get a smaller number when you OR things together. So you're not going to be able to get 1 from 5, 3, or 2 OR together. Okay. So with that said, let's think about how we're going to solve this problem. Well, you know, since we're dealing with OR, it seems like it's going to be fundamental that we understand how OR works. Now, I'm assuming that you understand how an OR operation works with an integer, but let's just quickly go over it and then look at a couple integers to determine maybe the nature of this problem and kind of a greedy approach to realize how this is going to work efficiently, right? Because, just as a side note, we can't try something like looking at every single number because nums of I is between 1 and 10 to the 9. So that means we'd have to look at 10 to the 9 numbers, which is already going to give us a time limit exceeded, right? Because generally we can solve problems with constraints where our total runtime is somewhere between 10 to the 6, 10 to the 7, and that's, you know, the edge. So we can't look at every single possible number, and even if we were to look at every possible number, which is already going to give us a time limit exceeded, we would have to figure out if that number is expressible from nums, and there's 10 to the 5 numbers. We'd have to look at all 2 to the 10 to the 5 possible combinations to determine if that number is expressible or not. So that means we have to look at all 10 to the 9 numbers, and for each all 10 to the 9 numbers, you have to look at 2 to the 10 to the 5 possibilities. So for a total runtime of 10 to the 9 times 2 to the 10 to the 5. So that's a little bit outside of the realm of possibility. I think that would take my computer more time to solve than the entirety of the existence of the universe going backwards or something crazy like that, because that's an astronomically large number. So that's not going to work. So we need to look at some sort of relationship of OR and these numbers to determine if there's something more efficient, right? So when we're looking at OR, how does an OR work? Well, if you have 2 bits, A or B, right, a number can be expressed as a sum of individual bits, right? If we have A or B, we can do the following operation on A or B, right? A or B. The only possible expressions for A or B are 0 or 1 or 0 or 1, and A are 0, 0, 1, 1. Now, when we do the operation A or B, if A is 1 or B is 1, it becomes 1, otherwise it's 0, right? So since they're both 0 here, it stays 0 here. Since one of them are 1 here, it becomes 1 here. Since one of them are 1 here, it becomes 1 here. Since one of them are 1 in this final position, in reality, both of them are 1, it stays as a 1 here. So this is the kind of truth table for an OR operation on an individual bit. If you had an integer like this, for example, that was represented like this, if you did an OR operation, you would get the following, right? Because you're just you're ORing each individual bit to get the resulting bit, right? Okay. So with that said, let us think about, let's think about how we're going to do this. So let's look at the first couple numbers as the integers of numbers as their binary form to determine kind of how OR would integrate into the representation of these numbers, right? So just for a simple case, let's look at 1 through 10. Okay, I'm going to start with 0 just so it's a little easier. And then let's look at the binary representation of these numbers, right? So going back to maybe grade school or intro to a computer science class, right, when we talked about binary representations of numbers, right, what we can do here is represent them using their bits by saying, well, 0 is 0 times all of these things. Let's do it in a different color, actually. 0 is 0 times all these things. 1 is 1 times 2 to the 0. 0 times 2 to the 1 plus 0 to the 2. 2 is 1 times 2. 3 is 2 to the 1 plus 2 to the 0, right? Sorry, I'm just remembering how to do this. This is 0, 1, 0, 1, 0, 1, 0. This is 1, 2. Okay, so this is the binary representation of these integers in the range from 0 to 10. I just selected 0 to 10 arbitrarily because I'm trying to make a point about how this is supposed to work, okay? So one thing you'll notice is you can represent numbers using the OR of their bases, meaning like 3 is really 1 or 2, right? Because if you OR these together, right, you'll get this as a result. Meaning if you take 3, it's really 2 to the 1 or 2 to the 0, right? 2 is just 2 to the 1. 1 is just 2 to the 0. We're going to ignore this one here. 4 is 2 to the 2. 5 is 2 to the 2 or 2 to the 0. 6 is 2 to the 2 or 2 to the 1. 7 is 2 to the 2 or 2 to the 1 or 2 to the 0. 8 is 2 cubed. 9 is 2 cubed or 2 to the 0. 10 is 2 cubed or 2 to the 1. So what I'm basically saying is you can represent a number just using the OR of these bases, right? And what you can also do is if you have 1 and 2 at your disposal, you can create 3, right? If you have 1, 2, and 3, and 4 at your disposal, if you have 1, 2, and 4 at your disposal, right? If you have, I guess what I'm trying to say here, because this is kind of the meat of this problem, the subtle nuance of how this works to help you get to an efficient solution, right? If you have 1, 2, or 4 at your disposal, from that you can create all of these numbers, right? Like, because if you have 1, 2, and 4 at your disposal, that means you have 2 to the 2, 2 to the 1, and 2 to the 0 at your disposal. So you can build 5, 6, or 7, or 8. If you have 1, 2, 4, and 8 at your disposal, you can create all the numbers up into and including 15, right? Because it's just some OR combination, right? If you have 1, 2, 4, and 8, all numbers from 1 to 15 are expressible with some combination, right? Some subsequence of that system, right? So regardless of what my system is, right? If I have this, for example, regardless of what those other numbers are, if I have 1, 2, and 4, that means I have 2 to the 0, 2 to the 1, and 2 to the 2. So with that, I can express everything from 1 to 7 by using some OR subsequence of this system. Okay? So if I have 1, I can create 1 alone. If my system has 2, then just from that I know I can create 3. If I have 1, 2, and 4, I know that with this system I can create expressible 5, 6, 7. And if I have 8, then I know I can create all the way up to 15, and so on and so forth, right? But I can't get 1, 2, 4, 8 as a combination of something else, right? Because 4 is just 4. I can only get 4 by itself. I can't OR anything else together to get 4, right? Same with 2 and 1 versus 3, it's an OR of the bases, right? Because these basey numbers are really important. So when we're solving this problem, what we can do is we can look at our numbers as a set, and we can say, if 1 is not in our system, then we return 1. We're done, right? Because 1 is not in the system. So, but if 1 is in the system, we have to look at 2. Okay, so now we're looking at 2, assuming that 1 is in the system. If 2 is in the system, then we can create 1, 2, and 3 using an expressible OR, regardless of what else is in the system, right? So then we look at 4. If 4 is in the system, then that means I've already established that 1 and 2 are in the system. So with 1, 2, and 4, I can create everything up to 8. And with 8 in the system, if I check 8 and 8 is not in the system, then I return 8. But if 8 is in the system, that means that 1, 2, and 4 are already in the system. So I can create everything up to 15, right? So the basic idea of this problem is just say, we'll say n equals 1. Check if n is in nums, right? If it isn't, if it is, if not, return n, right? Because that would be the minimum number we can create, right? As soon as we get to 4, if we got to 4, that means we checked 1 and 2. So everything below 4 is expressible. So then that would be the minimum number, right? Because anything to its right would be larger, and everything to its left we can already create because we've already established, if we're looking at 4, that 1 and 2 can be used to create everything smaller. So if not, we return n, else, I don't know why. So if n is in nums, we have to double n, right? We have to say n equals n times 2. Else, we return n because n is the smallest number, right? And that's because with the bases, you can create all the other numbers. And if the bases isn't in the system, that's the smallest such number you haven't seen, right? And everything that's smaller than it, since you're at this number, can be expressible with the bases. So the smallest such number that you can't find has to be one of these bases, and it has to be the first bases that you don't encounter, because anything larger would be larger than these bases, and anything to the left would be a combination of the other bases you've already checked. That's the best I'm going to be able to describe this. Okay, so the first thing we'll do is we'll turn nums into a set. That way we can check it in linear time. In constant time, right? And then we just keep this n variable and set it to 1. And then we'll say, while n is in nums, n times equal 2. And at the end, we just return n, right? Because eventually it'll exceed the size of nums. There you go, right? So the idea is essentially we're going to check the bases. If the bases isn't in there, then that's the smallest thing that's not in there, right? It's just an extension of this idea here, right? We check 1. If it's in there, then we have to check 2. If it's in there, then we know 1 and 2 are in there, so we would check 4 next. If 4 is in there, then we know that everything that's a combination of 1, 2, and 4 using these OR operations in there, so we'd have to check 8 next, and so on and so forth, right? That's the clearest way you can think about it, right? Anything smaller than what we're checking can be expressible because the previous basis is expressible. So just because we skipped over 5, 6, and 7, we know intuitively, not intuitively, but kind of like as a result, because these previous bases were checked, right? And then we wouldn't want to, if it's not in there, we wouldn't look at anything to the right, because anything to the right wouldn't give you the basis. So that's the basic idea behind this problem. Okay. All right. In terms of time, well, let's do space first. So for space, we just create a set that's the size of nums in order to give us a better runtime. So that's just O of n, because we have to create a set that's proportional to the size of the input n. And then for time, we are doing what? Well, n starts at 1, and it's going to be doubling every operation, right? So in the worst in the worst case, nums could be like the basis itself, right? It could be 1, 2, 4, 8, 16. So in the worst case, nums itself is the base. So you'd have to check if 1 was in there, then 2, then 4, then 8, then 16. So it could be the size of the array because every single n number is in there, right? But it could never exceed that, right? Because you're only going to, in the worst case, all the bases are all the indices. But that's the very worst case. So it can't be larger than that. Okay. Peace out, guys.